Hi, good morning, and welcome to the ZP vlog on, not vlog and podcast, ZP Developer Zone webinar. So we like to do this webinar once a week, and it's really just to kind of answer technical questions that have come in during the week. So let me be a bit more efficient with your time and go a little bit faster. So let me just say a few things. Don't forget the ZP Academy. There are at least 2 free courses on there where you can sign up and learn something for free on electrochemistry. There are the webinars. There are quite a few webinars during the week. I will cover those shortly. We do have collaborations. Even just last night I had a letter from a university asking for a collaboration. We do have essentially jobs, so we're a business obviously, and we do employ. And we have the ZB Developers on website, and we do have the workshops. The workshops are often in person, and we've got, I'll have a list of those workshops for you briefly. So in regards to workshops, if you see a link jump up, by the way, that means that I'll put the link underneath the video afterwards. You can find it. So don't forget, there's a workshop in Norway in November. I do want one of the inquirers, the gentleman regarding wire sensors, to come, but I know it's a bit of a distance. We do have a workshop in Coventry. We do have another workshop in December in Norway. Again, the guy on the wire sensors, if you can come, that'd be great. And there's one in Norway in December. So we do have a lot of workshops. There's a link, and hopefully you can find those workshops as well. We do have a webinar today. The times I'm showing here are actually Indian times, but you can sign up for the webinar today. This is on the Julie. I'll go quicker. And we do have these webinars scheduled as well. There's one on Julie. Julie's a cloud database, cloud management system for electrochemical data. Super useful. Sense it all. Even though I may be talking about screen printed electrodes today and protein A and protein G, you will find that the Sense It All platform is compatible with all those. We do have our food sense webinar. Food sense is an exploitation, or not exploitation, but an application of our Sense It All platform for measuring chilies and ginger. So we do have webinars on those. Don't forget, we also have a conference running in the UK in the 19th to 20th of June 2024 on the commercialization of electrochemical biosensors, and you can register for that. And we've already discussed this. We also do corporate workshops, so if it's a company and you can kind of bring together something like 20 or 10 to 20 people in a room, then it's probably worth having us come online. Sorry, not come online, but come on site and actually do a workshop on site. So the questions I want to cover today is, I would like to inquire whether you could have a biosensor for bacterial proteins such as protein A, protein G. Alternatively, can you immobilize those such electrodes? So I will discuss that today. And then somebody else is asking about a phosphate sensor. What's the detection limit detection? What's the selectivity, the lifetime of the sensors? And then also he spotted that on the website, some of the data sort of shows a positive of slope when we increase the phosphate, and that's because we've essentially taken the connections and put them around the wrong way, which is a little silly, but we've corrected that a little bit. And then I'm also going to comment about wire sensors as well. I'm also going to go a bit faster. So question number 1 about protein A and protein G. It's probably worth saying that protein A and protein G will bind or bond to our carbon electrode. So I've put a link here to the 501, which is our most recent carbon electrode. So if you take this electrode and you sort of drop cast onto it, try and keep the drop on the electrode. Don't let it spread out over everything else. It just makes a mess. It's not good, manufacturing practice to sort of spread it everywhere else. But if you take our carbon electrode, you can just do a drop cast, and the protein will stick to the surface. Don't use the platinum 501 because obviously we've got experience of binding protein A and protein G to the carbon, but we certainly haven't done it on the platinum. I can see there being a good affinity, and I can understand there's a good sort of hydrophobic affinity between carbon and protein A or protein G, but it's not the same for platinum, so don't use a platinum. But in terms of the carbon electrodes that I'm most electrodes that I am most sort of promoting at the moment, I would say the carbon 501 is a good one for you. Not the platinum 501, but the hypervalue carbon electrode is good for you. In fact, we've used that a lot. The only reason I'm suggesting the 501 carbon rather than the hypervalue carbon is just because I think people, especially in an academic setting, kind of prefer the circular electrodes because they could just do a sort of simple drop deposition on top of that. Don't use the hypervalue platinum, and the gold electrode is also not what I'm recommending to you. But these links, I will try and remember to paste these links underneath the video later on. But in summary, you probably need the carbon SPE or the hypervalue, sorry, the 501 carbon or the hypervalue carbon. Hope that really does help. And on that hypervalue carbon electrode, we have definitely done what you're asking. Here's some equipment. You probably need an impedance spectrometer if you're going to get into doing protein assays. You also probably need a cable between the potentiostat, and you also need a connector. So I've suggested the carbon 501. I've also suggested the hypervalue carbon electrodes. If you're in an academic setting, maybe just try the 501 because it's easy to deposit on, but then you will need a potentiostat, you will need a cable, and you will need a connector. And what's nice about our screen printed electrodes, even though we're having really an R&D conversation here, we can commercialize these things through our Sense It All platform. If you're unclear about Sense It All, I did say there will be a link underneath this video which will show you that there's some webinars on Sense It All, and you can attend those webinars for free. And I'll also put this link underneath as well. Also, I'm starting to realize that we're going to have to do webinars specifically on screen printed electrodes. So tomorrow I'm going to do a webinar specifically on screen printed electrodes. I've got a link here. Now the reason I mention it is because the biggest problem with screen printed electrodes, especially those that make it into the kind of academic market, is really reproducibility. So I'm really going to cover that. ZP makes the most reproducible screen printed electrodes that are kind of, you know, let's say for purchase of a web store. So I'll discuss that tomorrow. Question number 2 is really about phosphate sensor. Somebody was asking us about limits of detection, time of use, and also why our sort of axes, why our response was the wrong way around. We've shown like what's called a sort of cation response rather than anion response. I just want to say I have corrected the web page a bit. We have put a data sheet up there, and I have also put some data where, you know, we have connected the, I would call it the auxiliary electrode and the working electrode around the right way in this particular set of data. So the quick answer is now there is a data sheet up there, and there is data the way you would kind of essentially expect it. Just out of interest, this is all very silly, but if you have essentially a phosphate sensor is a type of ion selective electrode. If you connect the cables up correctly, then as you increase the phosphate, you essentially get a sort of signal where the potential is essentially getting, the magnitude is increasing, but it's increasing in a negative direction. But unfortunately, if the engineers in the lab wire up the wrong way, you still get the signal. It's just going in the opposite direction. It's a little bit of a daft mistake, but sometimes it happens. I did analyze some of our data because I was thinking about that limit of detection question that you were asking. So I was looking at this data and thinking, right, well, 0 is not a good, when you're doing ion selective electrodes, 0 is kind of daft because an ion selective electrode follows the Nernst equation. So your Nernst equation kind of says that signal is proportional to the log of concentration. Well, when you do 0, the log of concentration of 0 is basically infinity. So sometimes I try to get our guys not to test at 0, but maybe at 0.01. But that said, I kind of have a very little signal between 0 and 0.1, but we do have a strong signal. And no, actually that's not true. I must correct myself at this point. What's happening here is we've got 0, then they add 0.1 and we respond, then they add 1 and we respond, then they add 10 and we respond. So what that tells me is actually we do have a strong signal going from 0 to 0.1. Like I say, I'm not super keen that we test it at 0. I think we should test it at 0.01. But I did analyze the results by picking all this up, and I think we've got a sensitivity of approximately 31 millivolts per log to the base 10 of phosphate. Now, the data sheet and the data I have on the website is what we put into the public domain. What we do say to people is, look, here's quite a bit of data. Here's a free webinar where we try to discuss it a little bit. But what we do say to people is, look, you know, you essentially have to try and buy it. And so take a look at those links, and hopefully that's helpful for you. In terms of wire sensors, I do have quite a nice video actually where one of our engineers is showing her use of a wire sensor, and I have put the link to the video underneath here. And so she does talk through this. Now she's specifically at this case doing CGM, a CGM, continuous glucose monitoring wire sensor. It's quite nice actually because she's doing the challenges and essentially getting the signal accordingly. So there we go essentially. So I want to move forward a little bit. They're interested in pH, ATP, and ORP. pH is a potentiometric sensor, or we run it in open circuit potential mode. That's similar to what phosphate was earlier on in my comments. ATP, adenosine triphosphate, that's an amperometric enzyme sensor. ORP is an oxidation reduction potential. That's a potentiometric sensor, similar to pH and similar to the phosphate sensor. But we do all these in a sort of wire format. So amperometry is ATP, potentiometry is pH and ORP. Just out of interest, if you come to one of our workshops, we do cover all these techniques. I think the workshop is just the best way of actually getting a quick understanding of everything we do. I haven't mentioned today, we do have a single purpose biosensor circuit, so that is a good solution for anyone that's doing OEM, anyone who's trying to commercialize or is a bit of an engineer. You can use our single purpose biosensor circuit and it'll run all of these techniques. We do have the wire electrodes up on the website, and I should sort of just say that here's a link. Most of what we sell is actually the CGM sensor, the continuous glucose monitoring sensor. CGM is a well-proven sort of technology. There's a market for it. You know, it's $1 billion market. The way our CGM sensors actually work is if you pull apart a CGM, essentially, at least many of them have got two electrodes in them. They've done what's called shorting the reference with the counter. So when the currents are fairly small, you don't have to necessarily run a 3-electrode system. You can actually short together 2 of the electrodes. At that point, I start referring it to as the kind of auxiliary electrode, and then you've got the working and then this auxiliary electrode. We're quite experienced in this stuff because this is a entire sensor package that actually gets put into fish. We've got the sensor, the wire, and if you look very carefully, there's only 2 wires there that are twisted together going into a sensing package. It's a little bit complicated the way we do this now, I realize that, because we have, this is a picture that I kind of took out of the lab. We're connecting to the potentiostat, and we have a cable that connects to the potentiostat that ends in these kind of banana plugs. So here we have our counter electrode, our reference electrode, and those 2 get shorted together. So now the green one is actually ground. You don't need ground in this case, but you do need the counter and reference that get clipped together, so they're shorted. The ground you don't need. The working has to clip to the working. The next bit that we have is actually a cable that ends in this Molex connection. So we kind of have 3 cables, and I'm sorry about this. And then that connects to the sensor. So that all our sensors come with this connector. That connects to this. At the other end of this, we have some crocodile clips that connect to this, and then this connects to the potentiostat. I know that's a little bit kludgy. I know it can be improved, but it's what we have at the moment. And to be frank, it works. So we do make a pH wire sensor, and it works really quite well. So pH 8, pH 6, pH 8, pH 6, pH 4, pH 2, pH 4, pH 6. So this is a wire sensor. We're running it in open circuit potential mode, and it works quite nicely. We also have an ORP sensor. So here we're testing it at ferricyanide, 0.01 ferricyanide, 0.1 ferricyanide, and I should say molar here, and then 1 molar ferricyanide, so the ORP sensor. Also responds in potentiometric. The ATP, adenosine triphosphate sensor, which is actually patented, operates at minus 50 millivolts. There's a bit of a twist in this, that we do need you to have glycerol in the solution that you're testing, because the reaction with ATP requires glycerol. So that's a little bit of a sort of be careful kind of thing, that actually we do need that. So questions. Somebody just wants to essentially, I think, put protein A or protein G on an electrode. So I've suggested the hypervalue electrode. I've suggested the 501 carbon electrode. I've also said to you, look, you probably need a potentiostat, you probably need a cable, and you probably need a connector. And I have linked to all of those things. Phosphate sensor. So you can see that we've got a strong signal between 0 and 0.1. So our limit of detection, we haven't gone away and determined what our limit of detection is. I do have a data sheet there. The data sheet hopefully will be useful. But the data that I have is what we've put on the website or what I've put into the data sheet. And other questions about sort of longevity. It's not something I've done today actually, but in life there's four things that sort of have to come together. There's technology readiness level. So we make it a phosphate sensor, we manufacture it, so the technology readiness level is high. Then there's manufacturing readiness level, which is linked to technology readiness level. So we do manufacture that phosphate sensor and we do it on a screen printed electrode, so it's high. Then there's application readiness level. Application readiness level is what you are actually doing. So your application is your application. So we can sort of cover two of those bases, technology and manufacturing, but application is something that you have to essentially work on. And then there's business readiness level, which is probably too premature for this conversation. But I have updated the website and I have put a data sheet up there. And then comments on the wire sensors. The pH sensors are run in open circuit potential mode. The ATP sensor is run in amperemetric mode at minus 50 millivolts. And we do short together the counter and reference when running in the wire mode, and at which point I start to refer to it as the auxiliary electrode. And I want to say thank you. So if you've got any questions of ZP, as always, don't hesitate to reach out to us. As you can see, we do put a bit of effort into these slides. Sorry, it's a bit long sometimes, but as I say, and if you have a follow-up question, just reach back out to us. Okay, thanks very much.